You had a host go down last night. Thankfully, it came right back up. But when you go to look at the log file to find out what happened, there's nothing there. It's just blank wherever the failure should be. 1 minute, it's operating as normal, and the next message is that it's initializing and coming right back up. You've been asked to do an RCA to determine what happened and how we can prevent this from happening again, but without any log files, that's basically impossible. If this has ever happened to you, I'm hoping this video can help explain why. This isn't really about logging as a feature. It's about whether or not you can explain an incident. Can you prove a root cause instead of just guessing? Can you get a vendor to take you seriously? Can you correlate events across systems? Or are you just going to shrug your shoulders and say, we think it was storage, and move on? The failure isn't the crash. The failure is losing the only record of what led up to it. There are two assumptions at play here. The first is that any system that records logs will record the kinds of information that you need in order to diagnose an issue. After all, that's what logs are for, right? The second is that logs are log files. And since files are written to disk, that means that after a crash, they'll be available for you to investigate. I've worked with customers where the plan for a system crash was just to check dmesg, since that's what they use to troubleshoot the system normally. Dmesg is great, unless the system actually resets. Dmesg reads the kernel ring buffer, which zeroes out after a reset. Sure, you can use it to catch issues on an active system, but those log messages are gone after a crash. Dmesg is showing you the new boot, not the failure from the previous boot. Unless you've specifically configured something like pstore or RAM oops to preserve it, that data is volatile. Kdump has similar issues. First, you're assuming that the issue that caused the crash actually is kernel related. You're sort of working backwards. The same idea applies with checking the out-of-band management logs for hardware issues or the storage logs for storage issues. You're making an assumption about what the problem is and then working your way backwards. Now, if you don't have access to the system logs, your only choice is to go through these one by one. Not only is it very time-consuming, but what happens if you don't find anything? Is it because that component isn't responsible for the crash, or did the logs just not get recorded for some reason? Working your way backwards, you have no way to know. The ideal workflow is that you use the system logs to point you in the correct direction for what component might have caused the issue. There's a big difference between I searched kdump and I didn't find anything, and our logs indicate a kdump kernel issue, but I didn't find anything in kdump. So a more accurate model is that the logs will only record the information that you tell them to, and they'll only be durable if you explicitly make them so. And the logs that you do lose are probably the most important ones, the logs of what happened just before the crash. I'm going to focus on systemd-based systems using journalctl as an example. If you're using something else, the details change, but the failure mode is the same. If your logs aren't durable, you lose the incident. Now on systemd systems, logs can be stored in two places, under run, which is memory backed, or under var log journal, which is disk backed. If journal D is using run, those logs are in memory. They're gone on reboot. That's expected behavior. But even when logs are disk backed, they don't go straight to disk. Alright, so the basic idea here for the log files is that we have the application or the logging system has a group of log files. Those are going to be periodically written to the user space buffer. Those will then go into the kernel page cache. So they make their way here, they make their way down there, they make their way here. And then periodically, depending on the rate set, the flush rate, it will periodically flush these logs along with any other dirty pages in the cache to disk, meaning it'll actually write them to disk. So now they're sitting down here and they're safe. This goes into the kernel page cache. This goes into the user space buffer. And now let's say the system crashes. If the system crashes, then that means it'll no longer be writing to disk. It means it'll no longer be writing from the user space buffer into the kernel page cache, and the application will no longer be able to write to user space, depending on what's going on. But once the whole system is down, then none of this will work. So that means that anything in volatile memory, which means anything with these little dotted lines around them, goes away. So we lose this log, we lose this log. So now when everything comes back up, the only log file we'll have is this one. And any kind of log files that we had that might have indicated why it crashed probably wouldn't have been in this log. It probably would have been in one of these two. So you end up losing the very information that would help you diagnose why the system crashed in the first place. Okay, so looking at the differences between dmesg and journalctl in terms of the behavior that we've been discussing about losing log messages, the kernel diagnostics will be sending out messages into the kernel ring buffer. So these periodically start filling up the buffer like this. Once they reach the buffer, they're copied into both journalctl and to dmesg for access. So you can see them either way. So we can just copy that up there. Then we rotate these around and the exact same thing takes place. Just like that. And you can see that they're getting copied into the volatile storage for both dmesg and journald. Eventually, however, the kernel ring buffer will fill up. And when it does, it'll overwrite the previous message that was there. So once we decide to put message 4 in here, message 2 will replace message 1. We'll rotate around like that, and there we go. So you can see that the ring buffer itself has now lost message 1, and message 1 is still up here in dmesg and journald storage, but this is volatile storage, indicated by the little dashed lines. Journald, however, will take these messages periodically, and according to the sync rate, and write them to the journald database. So it'll take this message and stick it down here. And anything that gets written to the database is written to disk, and that gets saved. Dmesg won't do that. So now let's say that the system crashes. If the system crashes, then that means that it's not going to be able to write any of this to disk anymore. So anything that didn't make it to disk isn't going to be there. And all of this information, everything that is in volatile memory in both of these, is gone. So then when you come back up, you'll see that dmesg is only going to contain the new messages. This is after it comes back up. Once the system comes back up, then this will come through. Whoops. Then this will come through. It'll get copied to both of these. And now if you run dmesg, you'll only get message 5 after it came back up. But if you run journalctl, it'll pull this message from down here, and you'll see message 1 and message 5. But you'll notice that if it crashed before journald was able to copy the other messages, messages 2 through 4, into the database, then we lose them as well. Here's an example where I'm generating a group of test messages logging directly to journald. but with persistent logging turned off. Now I simulate a crash by simply powering off the VM and powering it back on. The system goes down and comes back up with a timestamp gap, but there's nothing to indicate why. journalctl only shows the current boot. dmesg shows initialization of the new boot, not the failure of the last one. What this issue looks like during an investigation is pretty consistent. If a system crashes and comes back up on its own, sometimes logs just go from a normal system behavior to suddenly starting to log the new boot, with nothing in between to indicate that there was ever a problem. Sometimes the logs are truncated or partially written. Sometimes they exist, but they're unreadable. It's just seeing a file full of null bytes. That's the signal. So, what can you actually do about this? First, make sure logs are disk-backed. Back to our example, that would mean that var log journal exists and that journal D is using it. Here's an example of journal D with persistence configured. We can see that it's using the var directory and not the run directory. We run our test messages again. This time we see both the current boot listed as 0 and the previous boot listed as -1. We can see here that this time it managed to capture the messages that we previously lost. Second, make sure that you've tuned the logging to the level that best balances system resources with the amount of information you need in case of system crashes. Set and agree on a level of detail that you require in an RCA beforehand, so that there are no surprises when there is a crash. The more rigorous the RCA requirements, the higher priority you should give to allocating resources to logging. Back to our example. Even if journal D is persistent, and on many systems it is by default, that only guarantees logs survive a reboot, not that you've captured the moments leading up to a crash. Now let's repeat the burst test, again with persistent journal D logging on. We get to 726 messages before I restart the VM. And we can see that we lose most of the journal D logging, even with persistence turned on. You can tune journal D to flush more frequently, but that comes with a big I/O cost. By default, 5 minutes is the maximum time journal D is willing to wait before forcing a write, although the kernel will typically flush its dirty pages every 30 seconds. Here I've changed it to 1 second, and now instead of capturing only 2 of our messages, we get quite a few more. The script runs again. This time the script makes it to 756 messages before I restart the VM. Now when we check journal D, we see that we captured 698 messages out of the 756 that were sent, a major improvement. My point isn't that you should set journal D to write to disk every second, and you probably shouldn't. It's that you need to determine the proper balance for your environment and then tune it before it becomes a post-incident issue. Third, test this under failure conditions. You'll notice in our previous example that even writing every second, we're still missing quite a few messages. You can never completely close that gap. simulate a hard reboot, simulate a crash, then check what actually survived. If you haven't tested it, you don't know how your system behaves. Of course, there are a lot more options out there for configuring logging, but configuration of all of them should follow the same rules. If they're not configured to be persistent before the failure, you won't have them. They all involve a trade-off of system resources versus log completeness. And since none of them can ever completely close the gap, you need to test them to see what information you will actually have post-crash. If you've had an incident where the logs weren't there, that's usually not bad luck. It's that most systems actually aren't configured by default to log the information you need to diagnose issues, or to save those logs in a way that you can build a proper RCA from, leaving the proper configuration of logging up to us. Thank you for watching, and I hope you found this video helpful. If you'd like any assistance putting together an RCA, doing log investigations, or if you'd like any one-on-one instruction on any of these topics, that's the kind of work that I do at futurerooster.com.